just So I hope you see now the bigger screen. Is that right? Or is the presenter mode that you're seeing?
Yeah, looks good to me.
Okay. Yeah, so thank you very much for the introduction, Sergey. I'm very pleased to be here today, and I would like to first thank all of you for attending the meeting, and then particularly Sergey for trying to accommodate as best my schedule for this talk. And I would like to thank you also for the opportunity to show this research that we have been doing over the last 4 or 5 years about the mobility of carbonate-rich melts within the deep carbon cycle. Before I go any farther, I would like to thank my co-authors, Xenia Ritter and Malcolm Matthew, for their work, because I'm presenting here as basically their results. And I would also like to thank the funding agencies who have provided support for these different projects. And the question is why we are interested in understanding the mobility of carbonate-rich melts, even though they are small fractions of the components of the Earth's interior, they play a key role, particularly within the deep carbon cycle. And this is something that I illustrate here with this figure, where you can see the major players within the deep carbon cycle, and the purple areas is representing the areas where we think we have the production of carbonate-rich or carbonatile liquids melts. And you can see that the area where they are focusing is particularly concentrated in between 70 kilometers and around 200 kilometers depth. These are the stability conditions or the optimal conditions where these liquids, they will be the major carriers for carbon and for volatiles, other volatiles like, for example, water, but also a range of incompatible elements. And
Carmen,
this, yep.
I really hate to interrupt, but could you please make it full screen? So something
I thought it was full screen already. Oh, it shifted again, actually. Now it's full screen?
Yep.
Okay, sorry, I thought it was before, and you say it was looking good. Anyways, it's fine. I keep going. Yeah, so this is the area where I was mentioning that is the most likely survival for the carbonate liquids in the mantle. Particularly, we know they are produced by partial melting of carbonated lithologies. And the problem we have below these 200, 250 kilometer depth is that the carbonate liquids, they will encounter a very reduced mantle, and therefore they will freeze into diamonds, and this is what we call the redox freezing process, while there will only become again liquids, carbonate liquids, when we have upwelling of this diamond-bearing mantle. However, we have evidences from diamond inclusions for residues of carbonated liquids, and these are inclusions of calcium carbonate, for example, in diamonds coming from the transition zone. What is indicating that the carbonate liquids, they can survive to greater depth than these 250 kilometers, and also that there are numerous heterogeneities, redox heterogeneities within the mantle that will produce these carbonate liquids. The question is how deep this production of carbonate liquids is taking place. And there is studies that are showing us that there is a barrier for the subduction of carbon to higher depth. And there is a focused region of melt generation that takes place within the transition zone. So most slabs that they will go undergo melting, they will be probably already quite depleted in carbon, what means that the stability range or most likely depth for the survival of these carbonate liquids will be limited to around 700 kilometers. So this is why we focus most of our studies on these pressure conditions that range below the transition zone at most. Just to summarize again a bit of what we know about these carbonate melts in the upper mantle is that they are stable around 200 kilometers depth mostly, but we also have eventual occurrence of these carbonate liquids to great depths because of the presence of oxidized mantle domains. The question is how these carbonate liquids move around the mantle is key to understand how the carbon is transported. And we know that they have very special physical properties. And some of the properties that are well known by now, at least qualitatively, is that these carbonate liquids, they have very low density and viscosity, which makes them very mobile within the mantle. Just keep in mind that the viscosity of carbonate liquids is close to that of water. Just to give an order of magnitude, the comparison with dense viscous silicate liquids. We also know that these liquids, they have excellent wetting properties, so they will impregnate and infiltrate the mantle quickly. And we also know that they have high electrical conductivity, which is around 2 orders of magnitude higher than the silicate liquids, that I will go back later on to show that this is probably one of the good diagnostic features combined with others that I will try to bring to the table later to identify or to discriminate between carbonate liquids and silicate liquids in the mantle by geophysical observations. We also know that these liquids, they have high connectivity, and this is something that has been shown by a limited amount of data that is available. They are way connected even at relatively low melt fractions that are present in the mantle and consistent with observations, and what means that they will have a clear signature to produce geophysical anomalies within the mantle. So despite all of this knowledge that we have accumulated over the last 2 decades about the properties of carbonate liquids in the mantle, we still have many open questions, and particularly we still don't know how carbon will migrate with the liquid because we are missing a quantitative description for the mobility of these carbonates in the mantle. These are the open questions that I will try to address. Obviously, I don't have an answer for all of them yet, but I would like to probably bring some new insights for discussion and some of the ideas for future work. And particularly, if we want to understand how carbon moves, and we need to know how these carbonate-rich melts are moving, how particularly changes of the chemistry of the melt as they migrate changes their mobility, and particularly this mobility is controlled by the density and viscosity. So the question comes to how the density and viscosity of the liquid is changing with pressure, temperature, and compositional changes in the mantle. The other question that we need to try to understand is what are the timescales for the carbonate melt migration within the mantle, and particularly if we want to try to map where these liquids are present in the mantle by geophysical observations, we need to understand what is the geophysical signature. And I'm not referring only to electrical conductivity anomalies, but also probably to some seismic anomalies within the mantle. One thing I would like to emphasize is that this quantitative understanding of the mobility of carbonate liquids has been quite limited because experimental limitations to determine both the viscosity and the density of carbonate liquids. And particularly, I show you this plot, which is quite revealing because we can see how in the last few years, the data on the density of, and particularly the pressure range for the density of the carbonate liquid has become quite expanded. And most of the data until the 2000s, it was quite limited to low pressures, while now we are able, thanks to some new developments on synchrotron-based techniques, but also relying on theoretical methods to determine this density and viscosity that was first limited by some experimental limitations that we all know, that is the high reactivity of these liquids, and also the problems to confine volatiles and the low decarbonation temperature that doesn't allow to apply some of the techniques that we are using commonly for silicate liquids. So my talk today will focus on some progress on theoretical predictions of carbonate melt viscosities. I will later discuss the density measurements that we have been doing on carbonate melt at high pressure and temperature, and combining the new density data with literature data. We are proposing also a first continuous density model for carbonate liquids, which allows to predict the density of multi-component carbonate systems that are more relevant for natural cases. And I will discuss also the implications of these results for the mobility, migration rates, and the geophysical signature of carbonate liquids in the mantle, and provide some perspective for future work. So one thing I would like to emphasize before I go any further is the compositions that we have been working on to show how relevant are they for the natural systems that are produced by partial melting of both eclogite and peridotite, and also from peelites. And this is a diagram showing the composition of melts that are generated by the partial melting of carbonated eclogite and peridotite, which are mostly alkaline carbonate liquids with different degrees of water content. And we have focused particularly on dolomite compositions and magnesite, both hydrous and hydrous compositions, to represent the partial melt use issue from eclogite and peridotite. But we have also added alkalis to our experiments to represent the compositions that are produced by the melting of subducted peelites, and particularly we have been working on mixed alkali and alkaline earth carbonate liquids, potassium magnesium and potassium calcium, that I will refer during the talk as alkaline melts. So probably a word that Xenia forged, but this is just to summarize the mixed components between alkali and alkaline earth carbonate. So these are the compositions that we have been looking at, and you will come back to them and see them over and over during the talk. The first thing I would like to discuss is some of the viscosity results. And as I said, this is probably a bit farther from my comfort area because I'm a experimentalist, but this we have got involved in dynamic simulation, molecular dynamic simulations, to compute the properties of carbonate liquids at conditions that we cannot reach easily experimentally. And particularly, we have applied classical molecular dynamic simulations in collaboration with colleagues from the Sorbonne University in Paris to determine the viscosity of these alkaline carbonate liquids that I showing you here. And we have covered high pressure range, which is difficult to reach experimentally, like 13 GPa and up to 2000 Kelvin. And the particular advantage of these studies is that we are using optimized force fields for carbonate liquids that they were developed by our coworkers. We ran the simulations for relatively long times to ensure proper convergence of the simulations. And you can see here in this diagram the simulated viscosity, which is represented by the purple line. And we can see that the convergence is ensured because we reach a plateau in the simulations. Then we can fit this data and extract the viscosity at different pressure and temperature conditions. I'm happy to discuss a bit more later, but I will not go in more detail within the talk. But I would like to show you the results, and particularly for the potassium carbonate, potassium magnesium melt. We have equally the same behavior when we look at the potassium calcium compositions. But the interesting thing that you can see here is that when we plot the data in what we call an Arrhenian plot, which means the log of the viscosity as a function of the inverse of the temperature, we see that we don't have the linear behavior that we'll expect for an Arrhenian behavior, which means a strong liquid, but rather we have a departure from the Arrhenian behavior, which indicates fragility of the liquid. So this is, to the best of my knowledge, the first observation of this behavior within carbonate liquids. And you can see this pressure at linear evolution that is quite standard, though. We have fitted the data we obtained from the simulations with an empirical model to generate a density model that allows to predict now the viscosity model to predict the viscosity at different pressure and temperatures within the calibration range. And we can also derive from this viscosity model viscous flow parameters for the geodynamic modeling. So the model is now implemented in the way that it can be readily used and easily used for the simulations. One thing I would like to mention is that we can already start identify some trends in the compositional evolution of the viscosity. And you can see here that clearly alkali liquids, carbonate liquids, they have much lower viscosity than the alkaline earth liquids. And also that the data that was available up to now is showing no departure from the Arrhenian behavior, but basically because the temperature range that is covered by the studies is relatively limited. In contrast, we observed that when we mix alkali and alkali earth carbonate liquids, we obtain viscosities that are larger than the M members. And this might be looking counterintuitive, but it's also observed for some other liquids. So probably is the role of substitution of potassium in the structure that creates additional interactions that change the viscosity trend. So we can observe now that we can have non-Arrhenian behavior plus an increase on the viscosity when we have evolution from alkali to more alkaline earth liquids. Now, I would like to discuss briefly what might be the structural origin or the reasons for having this fragility on the carbonate liquids, because so far we have observed non-Arrhenian behavior in many different silicate melt compositions. So no constant activation energy, no constant activation volumes, but changes with pressure and temperature. And we can see in the case of the silicate liquids that are plot, some of them here normalized by the glass transition temperature, that we have a change from what we call strong liquids, which means they have a linear evolution of the viscosity with temperature, to other liquids that are following a non-Arrhenian trend closer to the one we observe for the alkali carbonate liquids. The difference between these liquids is the depolymerization degree. And you can see that there is a trend with change in the fragility or increase in the fragility when we increase the depolymerization degree of the liquids. This idea of a strong and fragile liquids it was introduced a while ago by Angel, and it's only reflecting the response of the structure of the liquid to changes in temperature. And in the case of carbonates, which are simple ionic systems, so it can be seen as the most extreme case of depolymerized liquid, if you want, and if I kind of use the language, you can see here that the ionic liquid, they are controlled by simple Coulombic interactions. So what means that when temperature changes, they can adopt a range of different orientations and coordination environments. And this has been shown by some molecular dynamic simulations in sodium carbonate liquids, where they observe that with temperature, there is the formation of low dimensional structures within the carbonate network. What means is that you will end up with, instead of rings of carbonates, with a change and triangulars and also tetrahedra of carbonates connected together. This means that the changes on this carbonate network is implying that probably more carbonate liquid, not only the ones that we have investigated, they might show this non-Arrhenian behavior because it's intrinsic to the carbonate network. What means is that we might need to be careful with simple extrapolations of the viscosity by Arrhenian laws, because we might be underestimating the mobility of these carbonates, and particularly at conditions below 7 GPa, so at range of depth where the carbonate liquids are the most present, particularly shallower than 200 kilometers depth. In these areas particularly is where we found magma chambers and extraction of liquids, carbonate liquids from mid-oceanic ridges, which means that in these cases we might be underestimating the mobility of carbonate liquids. So this is just a caution mode to try to prevent extrapolation of the viscosity of liquids using standard Arrhenian behavior, because we might expect non-Arrhenian evolution of the viscosity. So now I would like to go and show some of the results from the density studies, and these are experimental studies, and we are applying a technique that we implemented a few years ago in collaboration also with other groups to determine the density of the liquid by a method called the X-ray absorption or radiography combined with large volume presses. So basically what we are doing is to monitor the changes on the absorption of the sample when the pressure and temperature changes. So the density of the liquid is changing. And this is reflected by a simple relation that might be familiar to you, which is the Beer-Lambert law, which is showing the changes in the absorption of the X-ray beam at the beginning and after crossing the sample are related to the absorption coefficient of the sample and the density and also the thickness of the sample. So the absorption coefficient, the mass absorption coefficient is a property that is only depending on the atomic properties of the atoms that form the compound, which means that this relation, the ratio between the absorption coefficient and the density, holds independently of pressure and temperature conditions. So if we know the reference absorption coefficient and density of the sample, and we can measure that experimentally, we can obtain the density of the sample. And this is what we do in the experiment. In the Paris-Edinburgh press, we contain the sample in a diamond capsule. The sample is powder originally, and then we can melt the sample and measure the radiography image of the sample. And you can see here the diamond, the sample, and the other wall of the diamond capsule. There is enough contrast between the sample and the diamond to make proper density measurements. And what you have here is the platinum cup that closes and then closes the sample that is indented into the compression chamber to generate the pressure and to seal the sample within the capsule. And we also have a strong absorption with the platinum powder mixed with BN, boron nitrate, that we use to measure simultaneously the pressure and the temperature of the sample. And this is the type of data that we collect here, and we measure absorption profiles and this is the absorption across the cylindrical symmetry of the sample. And we can fit this data and we can obtain the absorption coefficient that then we can correlate to the density of the sample. So now I would like to show you some of the results. Particularly, we used these experiments to measure the density of hydrous and anhydrous liquids and alkali liquids. But I show you here first the experimental setup that we are using, and particularly here a picture of the Paris-Edinburgh press that we are using at Soleil. The beamline is called Sichet, high pressure beamline at the French synchrotron. And you can see here the imaging detector and also the diffraction detector for the calibration of the pressure and temperature, but also to monitor what is the status of the sample. So we can verify in situ that the sample is molten by the disappearance of the reflections characteristic of the sample when we increase the temperature, and we can ensure that we are collecting the data only on the liquid phase. So I show you now finally the results. And this is the study of the hydrous compositions, hydrous magnesite and hydrous dolomite liquids containing 10 weight % of water. And one thing I would like to show you is only the results so far from the magnesite, but I can discuss later with you the other results if you wish. And the dots are representing the experimental data, and the lines is a fit of the data by a Birch-Monaghan equation of a state that allows to generate a model to predict the density of these liquids, hydrous liquids, at the pressure and temperature of calibration. And what you have here is a picture of the sample recovered after the experiment. And surprisingly, these samples quench into glasses, which is something that is not expected for carbonate liquids that usually crystallize rather than form glasses. But we obtain a glass which allows us to conduct many different characterization analysis, post-mortem analysis that allows to confirm that the volatiles that were maintained in the capsule at high pressure and temperature conditions. We have combined these experimental results with theoretical calculations of the density of the dry counterparts, so the dry magnesite and dolomite melt, and then together we can obtain the partial molar volume of water, so the compressibility of water that is dissolved in the carbonate liquid. And the data is represented by the symbols. The lines is showing the fit for the Birch-Monaghan equation of the state. And most importantly, now we have a relation that allows us to determine the effect of water on the density of liquids over a range of from dry to 10 weight% of water. And particularly, we can use this new information to determine what is the effect of water on the mobility of alkaline earth liquids. And you can see here the results. We observe that from dry carbonate to 10 weight%, we increase by 25% the density contrast of the liquid with the rocks, so the surrounded rocks. So we are providing or increasing the driving forces to upward migrate the liquid. And we also observe that the mobility is increased by a factor of 3. And you can see the comparison between the mobility of carbonate liquids with basaltic liquids, which is significantly larger, orders of magnitude larger. And particularly an important consequence from these results is that water in the carbonatic liquid will enhance the mobility of the liquids, and therefore it will fuel carbon mobility. And might be looking trivial also, but at least now we can quantify what is the effect and the driving force for the upward migration of carbon in carbonate and hydrocarbonate liquids. I also like to show you the results that we obtained on these mixed alkali and alkali earth carbonates. And you can see them here showing that those are probably, particularly the potassium magnesium end member, the component that has the lowest density that has been measured up to now. And it's significantly lower than even the potassium calcium component, but particularly they are substantially lower than liquids that are produced by partial melting of peridotite liquid or basaltic liquids with rocks. And you can see that the density crossover that it has been predicted for carbonate and silicate liquid based on some data that hasn't been reproduced so far, it might not be possible because the differences in density are quite significant, at least in the upper mantle conditions. So we can exclude density crossover between carbonate and silicate liquid. But one important thing that we can do with these new results on the density of these compositions that are proxies for the melts that are produced by subducted pylites is to evaluate what are the time scales for the extraction of liquids from subducting slabs. And this is something that I would like to discuss in the next slide. And particularly, we examine what is the dynamics of melt extraction from subducting slabs. And here, this cartoon is representing the possible mechanisms for this migration process. And you can see that migration of the liquid can happen by porous flow, so along the grain boundaries in the rock, or when the supply of liquid is continuous and there is a significant accumulation of liquid, the liquid over pressure, it can break the rock cap and then eventually allow the propagation of these dikes, which are two different mechanisms with obviously different hydrodynamic parameters and also with different time scales for the migration of the liquid. So we have computed the segregation times in the scenario 1, which means the migration of liquid along the grain boundaries. And you can see here the results for low melt fractions that are characteristics of what is expected during the partial melting of these carbonated lithologies. And you can see here the comparison with different rocks. So the segregation rates compared to different rock compositions, probably we should focus more in peridotite and eclogite, which are more relevant. And you can see here that at around 150 kilometer depth, we have segregation rates that are around 2 to 6 meters per year. And just to give you a comparison, this is around 1 order of magnitude faster than what is estimated for destruction of basalts at similar conditions. On the other hand, when we discuss about migration through a dike, we need to consider the width of the dike. Faster migration happens along thicker dikes, obviously, and you can see that the range of velocities or melt velocities that we are discussing are around 10 to 300 meters per second, particularly when we have very large dikes of around 1 meter or 10 centimeters. We can later, with these velocities of segregation and separation of the liquid, we can calculate what will be the time scale for the migration of the liquids. And again, we have a scenario 1 and a scenario 2. And here we have the migration by porous flow, which means a slow migration of the liquid. You can see that the liquid can take thousands of years to migrate, while in the case of the dike, we can quantify now what are the migrations, and you can have the ascent of this liquid if there is no interaction with the wall rock within hours back to the surface. Of course, the time scales are quite significantly different, but what is important is that even this porous flow migration on thousands of years is significantly fast compared to the migration of silicate liquids, for example. And therefore, both mechanisms, even the porous flow or the dike propagation, it will suggest rapid and efficient extraction of the liquid from the subducting slab and the return of the liquid or the carbon back to the surface. So we have mechanisms that or mobilities that support the efficient recycling of carbon back to the surface, which means most of the carbon will be eventually not be subducted deeper than the transition zone and recover back to the surface. Now I will move into a more thermodynamic aspect of this talk, and is the presentation of the density model that we have generated over the last year. And I would like to emphasize again that we have in the last 3-4 years increase on the data from the molecular dynamic simulation and experiments on the density of these liquids. However, most of the data is focusing only on simple or binary carbonate liquids, what means it's difficult to apply this density data to model the mobility of carbonate liquids that are representative for deep lithologies or produced by the melting of deep lithologies. So we have started to compile the density data that is available and try to implement a continuous density model for carbonate-rich melts, complex carbonate-rich melts at upper mantle conditions. And what you can see here is the density, pressure, temperature conditions covered by the density data set, which goes beyond the transition zone. And here you can see the evolution of the density data with pressure. And we have a total of 880 density data points, both from molecular dynamic simulations and experiments that have been included within our density model. And I show you here some of the characteristics of this model. We have tried to keep it as simple as possible, and we have formulated the model in terms of oxide components to describe the different volumetric properties of the carbonate liquids. And these are the range of oxides that have been included in the calibration from water and also CO2, obviously, but mostly alkali and alkali earth components. We assume ideal mixing in volume between the different components, and we haven't found big arguments against this assumption so far. And we also use a volume explicit Monaghan equation of a state instead of a Birch-Monaghan equation of a state, for example, to describe the volumetric properties of each simple oxide, because these volume explicit equation of a state are much more simple to handle than the non-volume explicit. We now have also implemented a user-friendly calculator, because the idea is that the community can use this density calculator, and also that it can be easily coupled with geodynamic models to determine the evolution of carbonate liquids in the mantle. So this is the performance of the model. I show you here the density predicted compared to the density that is observed, and we see a very good correlation. Most of the data is reproduced with residues that are lower than 0.05 grams per centimeter cube, and we also have density predictions that are made for most of the data set, which is less than 5%. So some deviations that we observe here probably are more related to heterogeneity and difference in the input data sets rather than to departures from the linear mixing volume that is assumed during the implementation of the model. We also can show here how well the model performs, and for here you see the predictions of the model, which are the lines compared to the data that is available for simple and binary carbonate liquids, and you can see that overall the reproducibility of the data set is very good. But we can also now visualize the relative effect of different components in the system. That was something difficult to visualize from the individual data sets. So we can see, for example, that again, water and alkalis, they always decrease the viscosity of the liquid, the density of the liquid, sorry, while the alkaline earth components will increase the density of the liquid. It might, again, look trivial, but at least now we have a model that allows to quantify or to put numerical values to this effect on the density of multi-components liquid. So with this model now, we can start looking at real carbonate liquids within the deep carbon cycle. And what you have here is a compilation of the different experiments that have been done to determine the composition of partial melts from carbonate-bearing mantle lithologies, either P-lites, eclogites, or peridotite compositions. They are summarized here. Those are only water-free because quantification of water in some of the experiments is not very consistent, and also because for most, and also is coming only from experiments because most of the natural records are always difficult to interpret. We need to adapt our model that is only calibrated for carbonate liquids to take into account the effect of silica and iron, which are other components that are important in a natural system. And so we have modified that by adding some thermodynamic constraints on these oxides. And we can here now see the predictions for the density of mantle carbonate liquids. And you can see that the most important effect, it comes from pressure, basically, is the bigger driver from the changes in density on these liquids rather than compositional effects or temperature effects, as you can see here. Another thing that we can do now with this model that we have implemented is to monitor the seismic velocities of carbonate liquids in the mantle. And this is done by using our equation of state data, and we can determine the compressional wave velocities. And you can see here again the predictions of the compressional wave velocities for the whole data set that is available as a function of pressure and temperature and composition. And again, pressure is the main factor affecting the changes on the velocities rather than compositional or temperature changes. So just to summarize these observations, pressure has the largest effect on both the density and the compressional velocities in opposition to temperature and composition for natural liquids. Now, we can also determine what are the implications of these observations, or I can discuss the implication of these observations for the geodynamic signature or the seismic signature of carbonate liquids in the mantle. And what you have here is the density that is predicted as a function of depth, and particularly the density contrast in between liquids that are produced in equilibrium with eclogite in red and with peridotite in green here compared to the mantle, so the average mantle that is calculated using the software Perplex. This data is calculated with our model, of course, and we can see that there is a decrease in the density contrast as pressure or depth increases, because the liquids become more compressible and then they increase the density faster than the solids will do. What is meaning this observation is that when we are at shallower depth, we will expect an enhance in the mobility of liquids because we have an increase of the density contrast with the rocks during the upward migration of the liquids. On the other figure, you can see the evolution of the density with the velocities with the depth, and you can see again in red the liquids derived from an eclogite, carbonated eclogite melt, and then you also see in green from a carbonated peridotite liquid. You can see again the velocities predicted for a mantle, average mantle composition, and again you also see that there is a decrease on the velocity contrast as depth increases. And another interesting observation that we have from this figure is that the seismic velocities of carbonate liquids seems to be higher than those of the silicate liquids that are observed here. And this is the diopside liquid in contrast to the carbonate liquids from experimental studies. These are the prediction for more complex liquids, but we have faster velocities than for the silicate liquid data that is available. What means is that carbonate liquids are seismically faster than silicate melt as far as we can predict from our observations. What means that also combined with high electrical conductivity of the carbonate liquids, it will be probably a good method to discriminate between carbonate and silicate liquids produced in the upper mantle. We have areas in the mantle at around 150 kilometers depth at the lithosphere-stenosphere boundary, where we have seismic anomalies and also electrical anomalies, as I showed you in the introduction, that is difficult to assign to one type of liquid. It could be equally well silicate liquids or carbonate liquids. And the fact that the carbonate liquids have a high electrical conductivity combined with faster seismic velocities, so will make lower effect on the seismic properties of the mantle, will be probably a good way of discriminating between this carbonate and silicate liquids in the mantle. So I'm arriving now at the end of my talk, and I would like to draw the following conclusions, basically which show that a combination of experiments and classical molecular dynamic simulations is an excellent way to improve our knowledge on the density and viscosity of liquids, carbonate liquids in the mantle at mantle conditions, and both dry and hydrous components that are more relevant for natural systems. We observe, based on the results, that we have an efficient recycling of subducted carbon, which is the result from a rapid extraction and upward migration of carbonate liquids at high pressure and temperature conditions. And I also present you the first continuous density model for multi-component carbonate systems that is valid for conditions that go beyond the transition zone, so covering all the possible conditions in the upper mantle transition zone that where carbonate liquids are predicted to be stable. And therefore, we expect that this kind of tool will be standard for geodynamic modeling of physical properties of carbonate liquids in the mantle. We also identified some diagnostic features from the discrimination between carbonate and silicate liquids in the upper mantle, and particularly the high electrical conductivity of the carbonate liquids combined with the seismic velocity, elevated seismic velocities compared to silicate liquids will be probably the best argument to discriminate between the two compositions. Before I go, I would like to finish with some perspective, and I would like to show you this figure where we see the data that is available for the density of liquids that are changing and evolving across the mantle. And particularly, we have now a lot of data for carbonate liquids, but there is a big range of melt compositions that are stabilized within the mantle by migration of the liquid, during the migration of the liquid, that are not known at all. So there is conditions that are uncharted, and particularly this corresponds to carbonated liquids and also transitional melts, that is including kimberlite liquids, which are diamond-bearing melts. So it's important to extend the type of experiments that I have shown you before to cover a range of conditions that are representing other melt compositions that are stable or stabilized within the average mantle. And of course, we need to have a better constraints on the migration process of these liquids and what is the geophysical signature to determine how are the rates or the fluxes of carbon coming back to the surface. And particularly, we need to have more experiments on how the liquids migrate within the mantle, and particularly how melts are connected within the rock matrix. And this relies also on advanced microanalytical techniques that are evolving and becoming available more and more often these days. So I think I will stop here, and I will be ready to take your questions and your comments. Thank you.
Thank you, Carmen. This is wonderful. This is so exciting. This is very exciting to me on several levels. One of them is that it renders some of the research that I plan to do in the future a bit irrelevant. So with that, I'd like to give the opportunity to students to ask their questions. If do we have a volunteer to go ahead? Does not seem to be the case. Well, then maybe we open up questions now for everybody else. So if you're not a student, please go ahead and ask your question now. Yeah, so while it seems to be a bit of an energy barrier here to overcome, I think I'm going to go with my question. So I'm really excited to hear about these MG CO3 glasses, and I have a series of questions about them. So my first one would be, how stable are they at ambient conditions?
Okay, so I mean, I haven't looked at them for a year probably, but they were pretty stable. You could measure them on the microprobe. We could recover them. We polish them on obviously hydrous conditions to prevent contamination and solutions, but they could be recovered. And some of them, I can probably show you, if I can stop sharing, I can, I don't know how I go from presenter to non-presenter mode. Well, probably I have a figure here where you can see the different things that we have recovered from the diamond capsule, and you can see some of those. This is the one I was showing before from the hydrous carbonate, magnesium carbonate liquid. We have even made glassy hydrous carbonatite, which I was very surprised to see. And then some of those, like hydrous dolomite plus 5% of silica, some of those they were polished and then take it back to the synchrotron to measure the absorption as a reference. So they are very stable.
Yeah. This is really interesting. I think I want to get back to you on these after the presentation. So do we have further questions from the audience?
Yeah, from me. So Melanie Sieber, are you still there? So we also did experiments, hydrous carbonates, and we did not observe glasses as quench product. I don't know the difference now, but we should discuss this.
Yeah, I mean, one thing I want to show you here, can you see the screen, I guess?
Yeah, yeah.
Okay, so you can see here, this is the quench samples before opening the capsules, still on the diamond capsule. This is something that you can see here. You can see at the end how much sample is left after the leads, they go inside. We break the capsules and we try to recover the samples. But before we open, we just quench temperature and then we still do a diffraction analysis while everything is under pressure. And this is what is seen here in these patterns. And you can see that this blue one is the one that is showing the dolomite glass, so magnesite glass. But this one on the bottom is the dolomite glass. And the dolomite glass, we didn't manage, the dolomite sample is not a glass, it's a crystalline sample, actually. So I don't know if it's just a question of ideal PT conditions from which you quench. We never been very
maybe
careful on that. Probably we need to look a bit on the systematics of that. But yeah, I was surprised that from one sample we managed to make a glass. But I was thinking that is because the magnesium sample seems to be more prone to glass production, like, you know, from the potassium magnesium.
Yeah, but we also have magnesite.
Yeah. So I don't know, I think it's probably the pressure and temperature, and we never really paid too much attention to which conditions. We just quenched them when we felt that it was enough. And then we recover the glasses. And then you can see that there is still carbon, there's still water in the sample, and it's really glassy material.
It's amazing.
Yeah.
So
I was more surprised to see that carbonatites, they could also do that with hydrous carbonatite.
But this is wonderful, Carmen. I think this opens up many possibilities to study these samples at ambient and at high pressure conditions. So my other question related to these glasses is, I think this question needs a bit of an introduction. So you may know that silica, so fused silica, so silica glass, at ambient conditions, its structure is cristobalite-like. So cristobalite, a crystalline form of silica, is often or sometimes is invoked as an analog of the structure of silica glass at ambient conditions. But as you apply pressure on silica glass, it undergoes a number of transformations, and when you decompress, the glass you extract is very different from the glass you started with. It's now, so the decompressed glass, say the pressure of about 20 gigapascals would be, its structure would be much closer to the structure of quartz rather than cristobalite. So I wonder if the structure of this MgCO3 glass that you obviously extract from some high pressure is different, or shows any obvious differences to the structure of MgCO3 melt at 1 atmosphere but high temperature.
Okay, the problem you have is that we don't have a glass at room temperature to compare with, because we start with hydromagnesite powders. So then we melt them and then we quench and we get a glass. So I don't have any idea of how these will compare to a glass of these that hasn't been compressed. We haven't done also, we have not done also structural studies from diffraction, for example. The only reliable data we have on these glasses is Raman, which you cannot say is probing really the structure, is just confirming that you have something that is more like a glass, carbonate glass, and contains the volatiles. We haven't done any diffraction on this kind of components, because usually in the melt, either you focus on the experiments on the density or you do the structure. Sometimes do the two things at the same time at the end is not very productive. So we have focused mostly on obtaining densities rather than looking at the structure. In most cases also, the reason was this setup we were using, that we will not see more than probably the first neighbor. So we didn't have a Q range long enough to see differences in the structure probably. So I cannot say much more about the structure. Yeah, unfortunately.
Okay. Do we have someone who has another question? Yeah, so Sergio is nodding. Yes, please, Sergio, go ahead.
Thank you. It's great. I also didn't know of this possibility of making general composition glasses from carbonate melts. I believe that most of this is due to the relatively small mass of your compression device with respect to the large volume presses.
I will also say that was the part of the answer that I forgot to Monica's question, that probably if you were doing that in the multi-anvil, the quenching rates might be
extremely different. Yeah.
Yeah. So
yeah. But
here we just switch off the temperature and the assembly is much smaller. So yeah, probably you cross you cross the glass transition temperature easier. Yeah.
My question instead is about the comparison with the mantle, the computed density and velocity contrast, and so the comparison is with the average mantle, so like a normal peridotype.
Mm-hmm. Yes.
Okay, so really that is not like some more specific composition which could be considered as what remains after you extract a carbonate peridotype melt. It's just the average peridotype.
Yeah, it's an average mantle composition.
Okay.
To cover the differences with the different melts. Yeah.
Okay.
I mean, in any case, I think the changes in density of the solid, they will be so small and based on the small changes in composition. So I don't see a big difference.
Yeah, what would be the amount? So what's, because I don't remember, what's the amount of CO2 or H2O component in this source for this melt? Is it very small?
It's relatively small. Yeah, usually you have like well, the first, the rock will have like 100 something ppm of CO2. I cannot remember
so really,
exactly the number. So it's really small.
So it's really tiny. So the amount anyway is a very small amount. Mm-hmm. Okay, sure. The density is lower, so the volume is so one cannot make direct comparison between weight percent and volume, but it's not a large amount.
No. But the important thing is these liquids, even though they are in small amounts, because of the infiltration, they can change significantly the physical properties of the mantle. And we see that on the electrical conductivity side. Of course, on the seismic, there is anomalies, but I think it's very difficult to model. You can do simple mixing models on between a liquid and a solid, but this is not representing what is the actual effect. So I think if we want to really understand how the liquid migrate, and
the connectivity,
exactly. So this is something that hopefully we can explore.
So it would probably have
also with Melanie.
Maybe also in rheology it can have an effect, very localized. But okay, it's very intriguing, because I can imagine that anyway, if you want to, I can see very well the interconnectedness between the grains, but I don't understand much what's the scenario to make large fractures. So can you really have a large overpressure of this liquid without recrystallizing it? Like, can you really make a crack out of this?
I mean, I'm not a specialist on the field observations, but I think there are observations both by migration of porous flow, but also from fractures. So I think you need very, very specific conditions, and particularly you need disequilibrium conditions. Otherwise, the liquid will likely react very easily with the average mantle, and you will consume the liquid. But then you will change the composition of the liquid, so you still might have a liquid that is migrating. So this is the interest of trying to cover the whole compositional range to be able to predict what is the density of the liquid as changes with the composition.
And I have a final question.
Migrates, basically. Yeah.
I have a final question. So, do you have any mean to guess what could be the effect of non-linear, non-ideal mixing? At least an order of magnitude. Could you be very far off, or do you have any way to guess or not?
You mean from the model, density model that we are making? It's difficult. What I say is we have observations for the magnesium bearing, potassium magnesium bearing component, which are the ones that are a bit off trend. And there have been also from molecular dynamic simulations guess, or they propose that these might be not behaving linearly. So there might be some non-linear effects on the mixing. However, with the data that we have, we rather think that there is a disagreement on the data set, which will be the reason for this departure from the ideality, rather than real non-ideal behavior. So it might be, if there is a non-ideal behavior in the mixing, it might be very specific compositions, but it's are also the ones in which we have the largest discrepancy in the data set. So it's difficult to say.
So quantitatively, it's very difficult to guess. Okay. Thank you very much.
Thank you, Sergio. Do we have anyone else who wants to? Oh, Ingrid, please.
I would have a question. Thanks a lot. It was a very nice talk. Thanks a lot. From what I understood, so from your experiments and model, most of the carbon that gets abducted will go back up quite efficiently. Do you have any way to quantify how much will be, or how much carbon will actually be able to cross this transition zone and go further down in the mantle, or is it something that we cannot still constrain very much?
I mean, I particularly not sure if I can have a proper answer for that, but I think when they do the experiments, that when they see this, I think the slab is mostly when you see the data from Andy Thompson, you see that there is a decrease on the melting curve. So at the end, even cold slabs, they will cross this melting curve. So I think it's quite efficient, the decarbonate, I mean, the melting of the, or at least the incipient melts, it will be quite efficient. So I will assume that, or consider that it's extracting most of the carbon cargo. Right. But doesn't mean that it's probably not redistributed differently, because once it's in the mantle, and if it's surviving this freezing, redox freezing, it can be still, but I will say probably the transition zone will be like a barrier.
Like a real barrier for carbon, yeah. Okay, thanks a lot.
Thank you, Ingrid. Okay, we have our next question from Thomas. Would you please unmute yourself?
Yes, thank you. Apologies if you did say that, but because I missed some parts of your talk. Did you include iron in your model? If I recall correctly, your model was free of iron, and I wonder what would change if you include iron.
Yeah. Yeah, we didn't include the iron because there is no data for iron-bearing carbonates in general, because experimentally they are not the easy compositions, because they alloy with the platinum, for example, of the capsules. So there is no really data available, but we have that on natural compositions. So we need to implement constraints for the iron thermodynamics in the system. And what we did is to use iron oxide as, or magnesium oxide as an analog for iron oxide. So basically we imposed for the iron component the volumetric properties fitted for the magnesium oxide. Yeah.
Okay. You also made a comparison with the electrical conductivity. The melts that you plotted, for which you plotted the electrical conductivity, did they include iron-bearing melts, or were they,
I was checking this morning. I cannot recall exactly, but I don't think they were iron-bearing liquids. They were iron.
Okay, so you would still expect a stark contrast.
Yeah.
Okay.
Yeah.
Okay, thank you.
Yeah, I think some of these carbonates that were measuring the electrical conductivity, they were magnesite or calcium carbonates or alkali carbonates rather than more liquids in equilibrium with peridotites.
Okay, thank you.
Thank you, Thomas. Okay. I still have a question, but I would rather have someone else ask their question if we still have someone who wants to ask a question. If no, well, so Carmen, you had this slide where you showed the densities of different carbonate liquids as a function of pressure. And if you could go back to that, I think it would help me ask my question. Well, yeah, so where you plotted the density of this potassium magnesium carbonate at the temperature of 1400 Kelvin. So there was a compression curve.
Let me just check where I am, because I don't know why I cannot move slides. I think now I closed everything. I should be fine now. Let me see. Which one was that?
I think it didn't have a number, or I didn't see a number on it, but I think it was towards the end.
Oh, okay, I know which one. You probably mean this one.
I only see the title slide.
Do you remember what it was? A plot of?
So it was a plot of. So you plotted density of various carbonate melts as a function of pressure, but also temperature and composition. Yeah, well.
Yeah, it's not this one.
But Carmen, we only see the title, so it's.
No, I see this slide.
Yeah, I'm also seeing the correct slide.
I see the slide, but not in presentation mode.
Yeah,
exactly. That's true.
Yeah, this is fine now.
I don't even see the slide.
Is this a slide, the one you mean?
No, but
I believe it's the one he means, but he cannot see it.
I don't see it. I only see the title slide.
Okay, but
doesn't matter. But okay, my question is, so you have these data for the compressibility of potassium magnesium carbonate at the temperature of 1400 degrees Kelvin, right? And these come from a model, from some experimental data, but then they are all, this data is put together to a model. So, but we do have, there is data in the literature on the compressibility, on the density of the exact same carbonate glass at room temperature. So have you compared this compressibility compression curve, this density curve to the glass density for this composition?
I think so far the only one that I know there is glass density data is for the potassium magnesium, probably.
Yep. Yeah, so this is for the potassium magnesium system from the paper I have in mind is Wilding et al. In Scientific Reports from a couple of years ago.
Yeah, yeah. Actually, I haven't compared the density, but I think that all the calculations they did, it was on the glass. It was not in the liquid phase. Is that right?
It was measurement. Those were measurements on the glass.
Yeah. It was diffraction data, actually, I think.
Right.
It was the diffraction data. I know which one. No, I haven't compared with them. I should probably do that and see where the predictions. But I mean, I will predict the density of this liquid at conditions that the liquid probably will not be stable because it will be carbonate. So I don't know how relevant it will be.
Anyways,
unless I don't understand your question.
This is something we can talk about later.
Yeah, we can probably talk about that.
But it's too technical. Never mind.
I haven't compared to the Wilding data actually for the density, but I think they were also getting quite low densities for the glass.
Yeah, so this is the problem I have with their data.
Okay.
So it's the compressibility is anomalously low compared to all the other carbonate melts. Yeah, melts.
I don't know if you see now my screen.
No.
Someone can see that?
Yeah, I can see it.
Okay,
we can see your slide.
In the screen, I have here the potassium magnesium carbonate and the potassium calcium carbonate, and you can see that even the potassium magnesium carbonate, as I said, is the lowest melt density that has been measured so far as I can say, because even at 1400 K, which is not high temperature exactly, the density is already like 1.6, 1.7 at 2 GPa, which is pretty low, I would say.
Carmen, it's okay. I'm just creating confusion here for everyone.
Yeah.
Again, you can come and watch my screen.
Yeah, well.
Yeah, just 2 meters far from here.
I can also watch the recording of the presentation afterwards.
Yeah, I don't know what is the issue.
Yeah, that's on my side for sure. So yeah, I'm out of questions. Let's call this the final opportunity to ask a question. And if we don't have anyone who wishes to do so, then I suggest we thank Carmen once again for this wonderful presentation and opening our new seminar series. Thank you so much, Carmen. It was a great pleasure to have you.
Thank you. Thank you very much for having me here. And keep in touch if you have any more questions about the glasses. I mean, probably was one chance to get these glasses synthesized. I don't know, really, we never searched really for them, but probably we try to reproduce is not doable. Who knows?
No,